Welcome, everyone. We'll get back to that problem, of course. There'll be office hours today right after class, so I encourage everyone to stick around if you would like to do that. Are there any questions? There should be grades for problem set 2 up now. And I think solutions either now or very soon. Any more questions? On our one course announcement. Okay. Great. Well, let's get started with our third class on probability, doing some other things. But first, there was a really good question in the Slack about conditional probability and independence. So I wanted to go through that. If P of A given B equals P of A, are A and B independent? Yes. It is, in fact, an if and only if. We can write it down like this. So intuitively, it makes sense that knowing B doesn't help us, doesn't change the probability of A. That means that they are independent. So you just write this down. This is what the definition of P of A given B is. And if you substitute in P of A for P of A given B, then you just have the definition of independent ifs. Okay. So the reverse is true too. As I said, it's an if and only if. So if they're independent, then P of A given B equals P of A, and also P of B given A equals P of B. So it goes both ways. I know it's weird sometimes to think of P of A given B and P of B given A in certain cases. For example, it's, you could think about the probability that it's going to rain given that it's cloudy right now. But you could also think about the probability if you didn't know that it was cloudy right now, but you did know whether it was raining. You could do the probability of B given A as well as the probability of A given B. Even for something in the past, if you didn't know whether it was cloudy earlier today, you could still think about the probability given that you knew that it rained later on, for example. Okay. So we're going to start out with entropy. Here's an intuition for it. The basic idea is how much information is needed to represent events from a probability distribution. So you have 4 events, each with probability 1/4. And so I'm going to assume that these are like different values of a random variable. So like there are 4 possibilities for this random variable, and each of them is probability 1/4. Well, a compressed way to represent them is a 0, 0, 0, 1, 1, 0, or 1, 1. And they all have equal probability, so it sort of makes sense to think of all of them just being like, all encoded by these different sort of symmetric strings. And so if you wanted to tell somebody, oh, well, the second one happened, you would just have to tell them 0, 1. So that requires 2 bits of information. Now, if you have 8 events, each with probability 1/8, it would be 3 bits because you would have to do something like 0, 1, 0, 1, 1, 0, 1, 1, 1, so on, all the 8 possibilities. So it would be 3 bits of information that you'd need. And in general, if you have probability p, assuming it's a power of 2, you have log base 2 of 1 over p. So in this, if you have probability 1/8, then there are 8 different events. So you have log base 2 of 8, which is 3. So if you just, the nice thing about logs is log of 1 over something is negative log of the thing. So you can do this. It's negative log base 2 of p. Okay. Now, what if the events don't have equal probability? Well, you can imagine sort of merging some of them together. And you can imagine merging them together, ideally in the best possible way, where you actually get a savings. So each, if one event has probability 1/2 and there are 2 of probability 1/4, then the most efficient way to do that would be to just say, OK, 0, 0, and 0, 1 are now both the first event, the first possibility. So I don't need the second digit. I just say 1. I just say the first digit, 0. So if I say 0 to you, you don't even have to wait for the second digit. I only have to tell you 1 digit. Whereas if I told you 1 as the first digit, then you'd have the option of 0 or 1 for the second digit. And so with probability 1/2, you use 0. With probability 1/4, you use 1, 0, and with probability 1/4, you use 1, 1. Okay. The total expected number of bits is, probability of 1/2, I use just 1. Probability of 1/4, I use 2 for this one. Probability of 1/4, I use 2 for this one. There's a question, if I have uncountably many events, then you can do an integral. I will describe what that is in a bit. But this is an intuition. So another example, if you have probabilities 1/2, 1/4, 1/8, and 1/8, then you're going to end up with the expected number of bits that you need being probability 1/2 times 1, probability 1/4 times 2, probability 1/8 times 3, and probability 1/8 times the other 3. Okay. So a generalization here is if you have different values of this random variable x, so mutually exclusive events, I guess I should have said. One of them has to happen. You look at the sum over all possible x of the probability that you do take on that value with your random variable times log base 2 of 1 over the probability. And then if you just pull out the 1 over, you get negative sum of p times log base 2 of p. Are there any questions about this? This is an intuition for why this formula might be useful. Now, this formula is going to become a definition. So if you're worried about what happens if you have uncountably many events or continuous random variables, you can think of this as the motivation for the definition of entropy. Because this is basically the notion of information, period. This is what information Shannon style is. Okay. So the entropy probability distribution is defined like that, only instead of using base 2, and some people do use base 2, use base e. It's easier to work with, and it just differs by a multiplicative constant. So the definition, entropy, is just this. And it's often denoted H. Sum over all possibilities for the random variable, probability of that times log probability. So this is using the shorthand p of x for p of the random variable equaling x. Isn't entropy the measure of chaos in a system? So entropy has different interpretations, though they all really do come from the same place. You can think of entropy as measuring the number of possible configurations, basically. So if from an information theoretic point of view, it's the expected amount of information you need to describe a system. The more possible states there are in the system, or the more possible states there are likely to be in the system, the more information you need to represent that. If you're thinking about it from the perspective of physics, then it can be a measure of sort of chaos. Because if you have more possible states, then you don't know anything about what the state is. So for example, a gas, you don't know where the gas molecules are. There are a lot of possible states. It's a probability distribution that is extremely spread out. That means that as high entropy as a probability distribution, it also means that as high entropy as a physical system. But I'm not really going to get into the physics of this. But they are there is a reason why the words are the same. Why is entropy always non-negative? Because it's a metric. Well, we need to prove. A metric is a word that means something. That's a word that you should be careful with, actually. But why? Oh, can we prove it? Like just from this formula. Yeah. The probability is always greater than or equal to 0. The log of a probability. So a probability is always less than or equal to 1. So the log of the probability is always, sorry, this should be less than or equal to 0. So every term in the sum is negative or at least non-positive. Sorry, that should be non-positive, and this should be less than or equal to 0. Forgot to include the equality. And yes, there's the interpretation of thinking about the length, the length of these strings that you would need to send if you were trying to send somebody information. That was the intuition. If you're doing it for a general probability distribution, there isn't necessarily quite the same interpretation, partly because what happens if something is not a power of 2. But yes, as an intuition, if we're taking number of bits you need to represent something, or number of nats that you need to represent something, if you're using base E, then it's definitely going to be non-negative. What if the entropy is 0? It's always non-negative, but it could be 0. You don't need any information to represent it. It's deterministic, so there is exactly one possibility. There's only one event with a non-zero probability, and that's p of x equals 1. So 0 uncertainty. That's when h of p equals 0. Great. And here is what happens if you have a continuous set of events, or continuous number of values for your random variable. You just take an integral here of p and log p. And I've been sort of eliding the fact that this is a probability density function instead of a probability. We'll get to that later in today's class. Questions? OK. There are n different values for x. What is the maximum possible value for the entropy? OK, we're seeing variations on a theme. Why is this true? Let's write it down. Suppose we have these probabilities for the different values. Then the entropy is just going to be equal to the negative sum of pk times log pk for all k. How do we get an upper bound for this? Great. Intuitively, we want this to be a uniform distribution. I agree with everyone. Why is it formally true? How do we prove this? I mean, sure, we could take the derivative. But it would be kind of a pain. Because there are lots of variables here. Like there are n different variables. We could do it with derivatives. And we would probably do it with Lagrange multipliers if we wanted to, actually. There's an easier way. When you're working with entropy, careful with arguments. Uniform distribution is the most random. Yes, it's true, but that's not really a proof. Intuitions are not always that good. Like, I mean, go with your intuition, but don't write a proof that's just your intuition. You could try doing things with contradiction, but there's a simpler way. What have we used in the past to prove inequalities? What are some inequalities? We don't have that many inequalities here. We could try using AMGM. Yeah, maybe. The logs kind of are a bit annoying. There probably is a way to turn this into AMGM. There's so many things that are really just AMGM. Yeah, so there's the other thing, which is Jensen's inequality. How could we use Jensen's inequality? What function would we apply it to if we had a function? Careful exponentiating things, because then if you exponentiated both sides, you would have these pKs hanging around. What's a function that we could use for Jensen's inequality? And there's a question about just plugging in 1 over n into the formula. Yes, you could do that, but you would need to show that that is the maximum. You're going to have a convex function. So let's just, let's pick a function and hope that it's convex, or that it's concave. And if it's concave, then we can do the same thing, just with a negative. So there's a lot of suggestions of log x or log 1 over x. The reason I don't like that is because our variables are pk here. And we have pk times log pk. So if we're going to do log x, we're going to have to deal with this hanging pk. Why don't we just try doing z log z? So z in here is pk. Like, is it concave or convex, or neither? It's, for a given function, it's probably going to be neither. Is it concave? Is it convex? It's a lot of disagreement, which is great. Cheers, I'm asking the right difficulty of questions here. Okay, so let's take some derivatives. We're going to take the derivative of just this one variable function rather than this whole thing. So the derivative here is just you can use the product rule, z times 1 over z plus 1 times log z. That's 1 plus log z. Take the derivative again, get 1 over z. So remember, convex means it's positive. The second derivative is positive. So this is convex. And it's really hard to remember which one is convex and concave. But yeah. So this is convex. So what's Jensen's inequality say? Well, it says that if we take the average of the values of z log z for all these pk, then we're going to be greater than or equal to if we evaluated it at the average. Now, why are we happy about this? This right-hand side seems really bad. Why is it better? Why is it better than before? Yeah, so they're probabilities, and they're all the probabilities for the possible values, and so they sum to 1. So it's just 1 over n times log 1 over n. And now if we, how do we finish this up? Well, just multiply both sides by -n. On this side, we get exactly this, exactly h. On the other side, we get -log1/n, which is just log n. And the inequality flips because we multiplied by something negative. So h is less than or equal to log n. Done. Is this value achievable? Good question. Whenever you show that there is a maximum value, you need to show that you actually get to that maximum value. Is it achievable? Yeah, now this is when you say uniform distribution. You plug in, or you could just like see the equality condition in Jensen's inequality, which is when all of them are equal. So all of them are equal to 1/n. And it's very easy to see that, if all of them are equal to 1/n, then it does actually attain this value. Any questions? Jensen's inequality is your friend, especially when there are logs. Logs are great for Jensen's inequality. Like seriously, like so many proofs about like entropy or mutual information or Kale divergence that are inequalities with those things. Yeah, so many of them are just Jensen's inequality. Could you use p equals 1 to show that this is achievable? No. If p equals 1, then as we saw before, h is going to be equal to 0, actually. So p equals 1 is sort of the opposite. It's actually the minimum entropy, which is 0. And you can think of these as being sort of the two polar opposites. One is you put all of your probability mass on a single thing. You have no uncertainty, so entropy is 0. The other is you distribute all of your probability mass as much as possible, and so you end up with 1/n for everything, and so that is actually the maximum entropy. Okay. And if you're trying to encode information about certain if you think back to our information interpretation, the intuition for entropy initially, it makes sense. Like if you're trying to give somebody a difficult task to convey information, you have n different things, it makes sense to spread out the probabilities because you're never biasing any one. If you biased any one, it would, there would be a savings. You would at least assume that it was probably going to be that one that was most likely. Question. If someone asked me any question about getting bounds on entropy, is this a good approach? It's a fairly good approach, honestly. Jensen's inequality is probably your best bet for a simple inequality that is useful with entropy. Because expectation is basically Jensen's inequality. Jensen's inequality is all about expectations. So conditional entropy. What happens if we know that x has a certain value, but we don't know what the value of y, another random variable, is? How much additional information is needed to get y? We're assuming that they're like correlated in some way. Yeah, something about x can give you a bit of information about y. So it's the same as before, right? Instead of writing down -log, sorry, there should be a probability there. -log probability that y is equal to y, you have -log probability that y is equal to y given that x is equal to x. Because you just know that about, you know the value of x. Okay. Again, sorry that there isn't a p there. So if we find the expected value of that, this is what this is called the conditional entropy. H of y given x. And this is pretty subtle. So what this is the expected value of the number of bits you'll need to express y given that you already know x. Notice that the expected value means you multiply not by this probability, not by this probability, the probability of y given x, but by the probability of x and y. Why is that? Well, because you're just trying to get an expected value. It's literally just the expected value of this as x and y vary. So we have, just move this negative sign out here, and we rewrite this log probability. I'm sorry, again, there should be a probability there. It's a conditional probability, so this is just the definition of conditional probability. And this is the definition of conditional entropy. And the motivation for it, again, is that it is the additional information that you need to get y if you already were to have known x. You can compare this to the standard entropy. It looks very similar, but here it's obviously a bit thornier with a quotient in the log. The questions? Again, you should convince yourself of why this is probability of x and y rather than probability of like y given x or something. It's basically, it's just because this is an expected value of the negative log. As with the standard entropy, we can show that the conditional entropy is also going to be greater than or equal to 0. That's just it's the same thing. Just the logs are going to be, negative, so yeah. Is there a version such that we take expectation over the conditional probability? That would just be the entropy. I'm not sure exactly. I'm not sure. I'm happy to think about that more. It's a good question. Okay, so now we have conditional entropy. We can define the mutual information. So the mutual information is defined as the entropy of y minus the entropy of y given x. I know this is like building more things on top of more things, but there's a reason for it. You can think of it as like how much. So y actually let me come back to the intuition for this in a moment. Let's first of all just write it out formally. Entropy of y is this thing, and the conditional entropy of y given x is this thing. Those are just the definitions. Sorry for all this thorny algebra here. This is just this first part is just literally the same here. The only thing that I did here was just change the summation to be over x and y, because it doesn't change anything. Just to put probability of x equals x, probability of y equals y. This is literally the same thing, just moved x equals x in there. And now, since both of these things are being multiplied by this, you can actually combine them. The logs combine nicely, and you get this formula at the end. So again, these are the two ways of expressing the mutual information. This is with thinking about it as entropy or conditional entropy, and this is thinking about it just with the probabilities. So there are some things we can take away from this. Oh, let's go back. Why can we write out py as probability of x, y? It's just because we're summing over x. If you sum this over x, you get this. Yeah, I just changed, I inserted a little x in there. So that's just so we can combine the two summations. That's all. Okay. More questions? Okay, so what can we learn from this? Well, first of all, if we switch x and y in the second definition, it's the same, because this is completely symmetric with respect to x and y. So that means that the mutual information x, y is the same as the mutual information y, x. We shouldn't take that for granted. For example, conditional entropy was definitely not symmetric. If you know the KL divergence, which we're not going to go into, that is also not symmetric. Mutual information is. And so this is also equal to the entropy of x minus the conditional entropy of x given y. And then here's the really cool thing. If x and y are independent, then this is just, the numerator and denominator are the same. So you have log 1, which is 0. So the mutual information is 0 if they are independent. So you can basically think of mutual information, the x and y, as being the information gained about y by knowing x, or vice versa. Let's think about this, right? Like, this is the total information in y. This is the extra information in y if you know x. So the difference of them is the information that you get about y from knowing x. And it's the same here. This is the information that you get about x from knowing y. And if they're independent, then of course that should be 0, because neither of them is telling you anything about the other. Questions? I'm going to leave 3 random variables to you. I'll leave that for you to look up or think about. Isn't what the opposite? I don't understand the question. So the mutual information is 0 when they are independent. So the information gained by knowing x is 0 if they are independent. I'll let you think about that. But yeah, it's hard to remember like which is the information you've already gotten, which is the information you haven't got yet. This is not the information that we gained. This is the additional information we need to write down y if we already know x. OK. So yes, question. Great. Can we get bounds for mutual information? Intuitively, it should be true that the mutual information is greater than or equal to 0. Indeed, this is true. I'm not going to go into proving it. How would you prove it? Just take a guess. Good. Yes. Jensen's inequality. So it's unfortunately not as simple as doing the thing with the thing that we were doing before, which is just saying that this is going to be positive or negative. It's not true that this is consistently positive or negative. Sometimes, for example, the probability of both of them is less than the product of the probabilities. Sometimes it's more than the product of the probabilities. But if you compute this whole thing, then it is always going to be greater than or equal to 0. Can we just say we can't make y more random by knowing x? I mean, short intuitions again, but this whole information thing is defined by entropy. It's not, you can't prove something about entropy and mutual information by recourse to our intuition about information, because the definition of information from a mathematical perspective is the mutual information and the entropy. OK, so I've been talking a bunch for the past few lectures about continuous probability distributions. Suppose you have a continuous valued variable x. I do want to just sort of say what's going on with this and why it's slightly different. So the probability that x is equal to some particular value, is basically always 0. For example, if you were to say, OK, what is the probability that this random person, this random person I picked, is exactly 2.000000003 meters high? It's going to be really small, basically. I mean, if they're exactly that high, it's going to be 0. So you can say, within a certain epsilon. What's the probability? But we don't really, how do you deal with a situation where P of x equals x is always 0? Well, you can think of a probability density function. And probability density function is not the probability that it's equal to that particular x, but it's something that you can integrate. So it is the density, if you moved around it a little bit. So if you said plus or minus epsilon, then the probability would be P of x times, in that case, 2 epsilon, because the length of the interval is 2 epsilon. So the way you do this is you integrate it. Between the probability that x is between a and b is the integral of P of x between a and b. And then the thing that we had before, where all the probabilities have to sum to 1, is we just say we take the integral for all the possible values, assuming it's a real valued variable, which I'm just going to assume is real value, is the integral of all the values is just 1. No. So P of x equals x is, yes, it is 1 over infinity. 1 over infinity is 0. It is literally equal to 0. It is just like 0.9999999 going on is another way to write down 1. 1 over infinity is another way to write down 0. Infinity is not actually a number, but to the extent that infinity is a number, if you write this as a limit, it is literally 0. I'm happy to talk about this more in office hours afterwards. And basically, this whole thing about infinity is another way of getting around the idea that math is, like, we have intuitions, but we really, in some situations like infinity, our intuitions are just slightly off. It's really hard to wrap our head around. And writing down numbers is a way to write it. Like, those are symbols that represent things, but the symbols can sort of mislead us. Anyway. So notice that P of x can actually be bigger than 1. For example, if you had like a delta function, really, really big, infinity, though it has to be non-negative, or there will be some interval with negative probability. If it's ever negative, then you just take a little bit of a little interval around that, and you're like, oh, what's the probability that I'm within this interval? And then it has to be then the probability is negative, and that will be terrible. You never want to have the probability being negative. But it can be bigger than 1 because it's a density function. You could imagine, you have a probability that's like very, very low everywhere, but it suddenly is peaked very strongly around this. If you take the integral, the area under the curve can still be 1, even if at some point the curve goes above 1, if that makes sense. Okay. So, examples of continuous probability distributions. The uniform distribution is the distribution where x is between a and b, so it's probability 0 outside there. But P of x is equal everywhere on this interval. So it's 0 outside, it's the same on that interval. What is the right constant value c for P of x? Yeah, so you can think about it as like an area under the curve. If you're thinking about it as area under the curve, the sort of the length of this interval is b minus a. And so if the height, this is a box. I'll draw a picture in a moment, but it's a box, and you're looking at the area of this box, and the area has to be 1 because it's a probability distribution, so it should be 1 over b minus a. But let's do this sort of, that would be perfectly fine, honestly, but let's just do it formally for the sake of practice. So 1 is equal to this whole integral. And since it's 0 everywhere outside a to b, we can just say that integral is a to b. In that case, this integral is just an integral of a constant. The integral of a constant is cx evaluated at b minus cx evaluated at a. So it's c times b minus a. And if 1 equals c times b minus a, then p of x is equal to 1 over b minus a. So this is, again, the plot of that. Questions? Okay. What is the mean expected value of the random variable x? You can think about it intuitively if you like for this one. I don't know what you mean by it's fixed. Yeah, so it is going, p of x is constant. P of x is constant, yes. Oh, sorry. That's a typo. I didn't mean to say what the mean is of p of x. You're totally right. I meant to say what is the mean of x. My apologies. The expected value of x is pretty clear that it should be the average here. So a plus b over 2. Though I know I also, for everyone who wrote down b minus a over 2, I actually first wrote down b minus a over 2, and then I felt very stupid. So the expected value is, like, just actually formally show that this is the case. The expected value is, again, it's the integral in this case of x times px. That's just what the definition of the expected value is. And I wrote it down on previous slides, but I wanted to give us an example of it. It's the integral here of x px. And so that's from a to b, so we can just write this down. Px is 1 over b minus a, so this is the integral of x over b minus a, which is x squared over 2b minus a, evaluated at b minus the same thing evaluated at a. If you work that out, it's b squared minus a squared over 2b minus a, which is just b plus a over 2. And that's, again, this nice factorization that you definitely should know, that x squared minus y squared divided by x minus y equals x plus y. It's really useful factorization. Probably the easiest and the most important factorization to remember. Okay. What about the variance? How would we go about doing it? How can we calculate the variance? What's the new thing that we need to calculate? We need the expected value of x squared. So what is the expected value of x squared? Let's calculate the same thing, but it's really simple. It's just basically, it is a similar integral to last time. Instead of doing x px, we do x squared px. And that's just going to be x cubed over 3 instead of x squared over 2. And so that's going to be b cubed minus a cubed over 3b minus a. And that's just equal to this. It's another factorization. That's good. OK, are we done? Is that the variance? No, why is it not the variance? We have to subtract something. We have to subtract the mean squared. So we had the mean. That was just a plus b over 2, the average. So if we subtract that here, and just do some algebra, we get b minus a squared over 12. That is an example how you would go about calculating the mean and variance of a distribution. In this case, it's a very simple distribution. It's not that simple, though. deceptively, actually involves some math to calculate it. Okay. And for anyone in machine learning who's wondering why there are like square root of 6 things turning up in initializations for like, some of the common initializations for weights, wondering why there's like a square root of 6 going on, it's because of this 12. It's because if you multiply this thing by 2 because of the ReLU, which changes the variance, then if you take the square root of that, you have square root of 6. For anyone outside deep learning, that's just an aside. Yes, that is for, well, he initialization is actually square root of 2, but. Okay. Univariate Gaussian. This is another probability distribution. The Gaussian or normal distribution, I assume that many of you have seen this in different contexts. This is the formal definition of the probability distribution. That is really thorny. I'm sorry it's so thorny. There's a lot of algebra involved in actually proving some things about the Gaussian. So I'm just going to state a lot of things about the Gaussian. They're not extremely difficult necessarily, but they're very messy, which is a pain because the Gaussian is actually is so super important. Like apart from something like the uniform distribution, definitely the most important distribution. So one can calculate with some thorny integrals that indeed you do have the integral of the sum of px over all possible x equal to 1. And you can calculate that the Gaussian has mean mu. This is this mu constant here. And it has variance sigma squared. This is sigma constant. Those are the two things that parameterize the Gaussian. So this Gaussian normal distribution is called n of mu sigma squared. Depends upon mu and sigma. And you would just calculate this basically in the same way that we did with the uniform distribution, only it needs a few integral tricks, basically, in order to deal with this exponential. But it simplifies nicely. The reason for this nasty constant of square root of 2 pi out in front is just in order that it normalizes correctly and that you get to 1. Okay, so there are various cool facts about the Gaussian. I'm just going to tell you a bunch of them. I'm not going to prove them, unfortunately. So suppose that you have independent random variables. We know that the expected values add in linearity of expectation, and because they're independent, we also know that, this should be x plus y. The variance of the sum of x and y is going to be the sum of the variances. Again, this should be a plus. Sorry about that. X plus y. But if they're Gaussian, it's better than that. Not only do the means add and the variances add, the sum is also a Gaussian. Formally, if you have x distributed by this Gaussian, y distributed according to this Gaussian, then x plus y is distributed by the Gaussian with the mean with the sum of the means and the variance with the sum of the variances. That's very nice. That's the first fact. Second fact, maximum entropy distribution. What does that mean? The normal distribution is the distribution with maximum entropy out of all distributions with mean mu and variance sigma squared. So if you were to fix the mean and variance that you want, then this is the best And then the highest entropy you get, most random, as it were. You can prove this with Lagrange multipliers. If you haven't seen that technique, it's totally fine. I'm not going to ask you to prove it. But you do a Lagrange multiplier thing, and you find just the maximum. Suppose you didn't assume the variance. What is the maximum entropy distribution if you just assume it as mean mu? So it's uniform if you are like, yeah, as wide as possible is somebody is commenting. Uniform as wide as possible. I didn't tell you what the upper and lower bounds are. So if you don't have upper and lower bounds, then you are in trouble. You could go all the way to negative infinity and positive infinity. So suppose that you had p of x equals 1 over n for n different values with mean mu. Or you can do a continuous analog of this, where it's uniform in like an interval, so where the mean is mu. The entropy is log n, as we saw before. But you can just take n to infinity, so you can make the entropy arbitrarily big. Oops. So yeah, there isn't a maximum entropy distribution unless you constrain the variance. If you constrain the variance, then you get a Gaussian. And then the final cool fact about the Gaussian is the central limit theorem. And in particular, among other things the central limit theorem implies, is that the graph of n choose k, for k varying between 0 and n, approaches the Gaussian. You can think of this as like the number of heads for n coin flips is going to be distributed according to a Gaussian. It's going to be most likely to be n over 2. And then there is going to be some variance of order n. It's a standard deviation of order n, square root of n. And so here you can see this is 100 trials of flipping a coin. The number of successes you get is going to be centered on 50, but it could also be 45, it could be 55. It's very unlikely to be like 20. And the distribution is pretty much a Gaussian. If you do 500 trials, then it's even more Gaussian. Here's 900 trials. Wow. Here you've got to scale them appropriately so that the standard deviation is scaled from, it's going to be square root of n over 2, we proved before. But we want to scale that down to just the same standard deviation so that we can line up all of these curves. More generally, the central limit theorem says that if you have the sum of some independent variables drawn from the same distribution, then you're going to approach a Gaussian regardless of what the distribution is. So it's basically saying that sample means are going to be Gaussian distributed. This is a really powerful result, which is basically the reason why everybody uses normal distributions and normal distribution confidence intervals and stuff in statistics. It's because if you're taking sample averages, they converge to the Gaussian, but it's not an obvious thing at all. The reason I'm not proving the central limit theorem is it's too freaking hard. Like if you want to go into it, you can certainly find a proof that you will understand, but it is not something that I can prove like in a few slides. And then finally, I just wanted to end, and feel free to go, but I wanted to end with just a really some indication of just how cool probability and randomness is. Random things in general, like we saw that the distributions converging to the Gaussian. Random things can be surprisingly predictable. Like given a large number of fair coin flips, the expected number is n over 2, but we'd be really shocked to get n over 4. It's going to be pretty tightly concentrated around n over 2. It's the same thing for big random matrices. You can prove things about big random matrices. Random matrix theory, I'm missing a word there. Random matrix theory is an entire field. And it's useful in many different applications like machine learning, but also quantum and many other situations. And here's one random matrix theory fact, which I just think is beautiful. So we know the eigenvalues of a real symmetric matrix are real. We proved that before. What are the eigenvalues if you have a random matrix and it's getting really big? So you're going to have infinitely many eigenvalues. You're going to have n possibly distinct, possibly the same eigenvalues. What are those eigenvalues? You have a distribution of eigenvalues. Let's assume each of the entries are taken independently of the others from a Gaussian. Gaussian, sampling from a Gaussian is like what is generally the best thing mathematically to do. These are the eigenvalues. This is a histogram of them. It's exactly a semicircle. I'm not going to prove it, but oh my gosh, probability can be really, really beautiful. It is office hours now. Next time, we will go into linear programs. I'm going to let you stare at this figure for a moment, though. Why do we make the assumption that the entries are taken independently? Feel free to go. This is office hours now, and I will answer any questions that people have.